This is a summary or overview of a maximum power transfer theorem, and it comes at the end of studying what I've called network reduction. So I go back to the beginning of this set of notes, and you see here that we've talked about 4 items. Let me swap these around here. They're not quite in the order that I talked about them in class. So we talked about linearity. We've talked about superposition. How do you solve circuits using superposition principles? We've developed the Thevenin and Norton theorems, and then source transformation in the middle of that to get from the Thevenin to the Norton. And then lastly, now we're looking at maximum power transfer theorem, which has relevance when we have, particularly after having looked at the Thevenin-Norton theorems. So, as you know by now, you can take any linear network, and if you connect to a pair of terminals anywhere on that linear network, you can model the terminal characteristics of that whole network by a single Thevenin resistance and a Thevenin voltage, and that will accurately predict the VI relationship at that terminal. So if you connect a RL across that terminal and you measure the voltage across that RL or in the current flowing through the RL, you can characterize or know what that network is going to provide simply by using an equivalent Thevenin voltage and resistance. So when we look at maximum power transfer, we're going to just look at a Thevenin equivalent because that covers this broader case of all linear networks. Now, what's the question at hand? What are we trying to do here? The question is, if I connect a load RL to a one-port network, a linear one-port network, that is what this Thevenin equivalent circuit is, and I'm trying to extract maximum power from that network to my load, what value of load resistance RL should I use if I'm trying to extract the maximum amount of power? So to kind of explore this the range of power that would be delivered to this load, let's look at 2 extreme cases. One, when the load is a short circuit, and secondly, we'll look at when the load is an open circuit. So the power delivered to the load, RL, is going to be the product of the current IL times the voltage across that load, VL. If RL is 0 ohms, then there can be no voltage across it. So we have 0 volts here multiplying actually a maximum current. It would be the short circuit current that we've learned about in studying Thevenin and Norton. So the power delivered to the load is 0. Okay. At the other extreme, where the load is infinite, open circuit, here we have the opposite situation. IL is going to be equal to 0 because any voltage across an infinite resistance produces 0 current. So once again we have no power, although we have maximum voltage. VL in this case would be the Thevenin voltage, or what we also call the open circuit voltage. So you've got those 2 extremes: maximum current when you have a short, maximum voltage when you have an open, and yet both those cases render 0 power delivered to the load. So we're going to expect that somewhere in between those 2 extremes is a power point, or a point of resistance value where the power delivered is going to be maximal. So that's what we claim, and we're going to pursue that. So the way that we do that is we write an expression for the power delivered to the load resistance, which is just the voltage across it times IL. And then what we want to do is replace VL, the voltage on the resistor, with the load line for our Thevenin network. So recall that we have a load line that would start at V Thevenin, or V open circuit. This is plotting VL now versus IL. We have I short circuit excuse me, at the y-intercept. The slope is going to be minus 1 over R Thevenin. Okay, and we can express the voltage across the load resistance as this load line. Okay, and actually, if I were to plot the VI relationship for the resistance, I would have something like this. So I would have a straight line with the positive slope for my load resistance, because the voltage across the load is going to be RL times IL, and of course the solution is right here in the middle. So now we have an expression in terms of just IL, and we now are going to take the derivative of the power with respect to IL, because we want to find where that derivative or that slope is 0. So we're thinking that if the power to the load is 0 at 0 ohms and out here at infinite ohms, then somewhere in between it must be maximum, right? Max and here. So let's take the derivative and find when the derivative, the slope, is equal to 0. So that's what we do, set it equal to 0. So now we have an expression that is in terms of IL being set equal to 0. And we find that the current at which point the power is maximum is going to be equal to 1/2 V Thevenin over R Thevenin. But we're after what is the load resistance value? What is the load resistance value at that point? Well, RL is simply V is Ohm's law, V over I. So we write RL as VL over IL, and then we take this IL expression and stick it down there and put it to use, and we take this expression right here for VL and we plug it in for VL. So now we have an expression that's explicitly in terms of well, it's not in terms of IL, because we also take this IL and stick it in there. I'm making this more complicated than it is, just some basic algebra. At any rate, we find the result ultimately that the maximum power is transferred when RL is equal to R Thevenin. And in fact, if you go to plot this, you find that it does look like this curve that starts at 0 and asymptotically goes to 0 at RL equal infinity, and there's a maximum power point right here, and that maximum power is actually V Thevenin squared over 4 R Thevenin. Okay, so if you think of it, if I have R Thevenin and the maximum power is transferred when the load is equal to R Thevenin, right, then what I really have here, and this is going to be V Thevenin, what I really have is I have V Thevenin across 2 R Thevenin, right? V Thevenin across that. So the power going to this combined resistance is going to be V Thevenin squared over 2 R Thevenin, right? But that power is being split between this R Thevenin and my load R Thevenin, so I really only get 1/2 of that, and that's where we arrive at the 1/4 term in our maximum power expression. So that's maximum power transfer theorem. As a final note, let me just throw around maybe 1 or 2 examples to help clear up some misconceptions. Okay, so let's suppose that I have a source, call it 100 volts, and an equivalent resistance of 1 ohm. Okay, and the question is, what's the maximum load power that I can deliver to a load? So think of this as being like a battery, maybe. Okay, a 100-volt battery has an internal resistance of 1 ohm. How much power can I extract out of this battery? Well, it's going to be when RL is going to be equal to 1 ohm. Right? And so the maximum power, you can do this 2 ways. You can memorize the formula, but the way I look at this is, hey, we're going to have R Thevenin and R load having the same resistance, so we're splitting the voltage. Right? It's a voltage divider. So I always end up getting half the Thevenin voltage to my load. or in this case 50 volts. So the maximum power transferred is going to be 50 volts squared over 1 ohm, which is 2500 watts. Okay. Now I'm delivering 2500 watts to the load. This is going to be to the load, but I also plus 2500 watts to our Thevenin. In other words, the network. So we have to remember that if we're thinking of, how efficient is this voltage source here? Well, it's only delivering half its power to the load. The other half gets burnt up in the 1 ohm. If that is a 1 ohm that's part of the battery, then you're actually putting 2500 watts, 2500 joules per second of heat into the battery, and that's probably not going to be a good situation. Here's one other example to test a misconception here. Let's say I have 120 volts, and here I'm going to think of this as being my house wiring, okay? And I have some wiring resistance, and I have a, let's say I have a 2 ohm load, okay? And I'll call this RW, the resistance of my wiring. And the question is, find RW that maximizes P power into the 2 ohm load. Now you might be tempted to say, this looks like a maximum power transfer problem, and maximum power transfer occurs when the Thevenin resistance is equal to the load resistance. So therefore, naturally, RW must be 2 ohms. Okay, if you'd said that, that would be, you would have fallen for my trick, because let's say that RW is equal to 2 ohms, right? Then we would have a total power delivered from the source of 120 volts squared divided by 2 ohms plus 2 ohms, right? So 120 squared is, what is that? I think 14,400 divided by 4, and so that would be 2272, 36. I might have a arithmetic mistake here, but 3600 watts, okay, into the 2 resistors. So you'd have 1800 watts to the load, half of that, okay? But I'm going to challenge that answer and say, no, actually I can get far more power. I can get 7200 watts into this load. How can you do that? Well, what if, why do I want any winding resistance at all? What if RW was equal to 0? Then I would have 120 volts delivered directly across my load, right? Which would be, I'd have now 120 volts squared over 2 ohms, and that would be 14,400 divided by 2, which would be 7,200 watts. Okay, so the answer is RW equal to 0. Now this might be confusing to you, but here's the difference. If you are given a network with a Thevenin, like a Thevenin network, where it has been specified the Thevenin voltage and the Thevenin resistance, and in this case that would be, you would be told what RW was, then the answer to the question, what load resistance value maximize power transferred to the load, the answer is when the load resistance is equal to the Thevenin resistance. But if the network, the Thevenin network, is not specified, if the question is actually asking what Thevenin resistance would you choose to maximize power to the load, in that case you're always going to pick the Thevenin resistance should be 0, right? Why would we want any resistance in our path on our way from a battery or a power source to the load where we're trying to deliver power? We never want any resistance or voltage drop in that path. So in that case we would specify the Thevenin resistance, or here RW, to be equal to 0.